To count off. All right, show me your boards, my friends. What you got? So, oops, I'm still frozen, aren't I? Boop. No. All right. C, B, D equals A. C, B, A, D, C, B, A, D, C, B, A, D. C bad? C bad. All right, so y'all said it. Now, do you remember that time? It was like, what, 2 days ago that I was like, oh, everybody got it right. Or everybody got it, and it happened to be right, and then everybody said the same thing, and then it wasn't right. So let's make sure that this is actually the right answer.
Not everyone got this one.
Oh. I think every board said that, didn't it?
No, Henry's board didn't.
Oh, okay, whatever. It doesn't matter. We're sharing kindness, and we're not making people feel bad. Okay? So, defend that answer.
Well, I know that A and D are constant, so they're equal.
So, you know that A and D, so what is it? Because A is at 2 and B is at 0. So, what do you mean they're constant?
They're not accelerating.
It's not accelerating. So what?
Force is 0.
Yeah, I forgot about it. So the work,
I'm not saying you're wrong. I'm just saying, what does that mean to you?
it means that there's no increasing or decreasing work being done. It's just like, yeah.
So in A and D, and the reason that I'm doing this, the reason that I'm trying to push you this way is because, I don't know, like on a test or on an AP exam, right? You have to not just be able to say, well, they look the same. You need to tell me what it means. So in the case for A and D, you said that they're not accelerating. So there's no change in velocity. So that means there's no acceleration. So what? Oops, that should be equal 0. That means that there's the net force acting is equal to 0. Is that what you're saying? And if the force is equal to 0, then how much work is done? Okay. Because we're saying that work is equal to force over a distance. And so even though it might be moving, there's no force, so there's no work. So work equals 0. Okay, so on A and D, you're telling me that the work is equal to 0. All right. How about for B and C? That's only halfway-ish there. Go, Nick.
C is accelerating more than B.
Tell me more.
And F net equals mass times acceleration, and so mass is the same. So the higher the acceleration, the more force.
So F net equals mass times acceleration. We're saying that it has a bigger acceleration, so it has a bigger force. Is that what you said? I just want to make sure I wrote it down what you said. Okay, so bigger acceleration, bigger force, more work being done.
Thanks.
And then for B, there is some acceleration, but not as much. Yeah. I find it absolutely fascinating that, and I don't know if you all did it this way, but kind of watching your heads bobble up and down, I'm gathering that most of you did. That is not at all the way that I approach this question. I just think it's kind of interesting. What's that? Explain. So you took this definition of work, right? Work is equal to force times distance. I took it from the other perspective. Work is also equal to what? Change in energy, right? I took the work energy theorem approach. So I said that work is equal to change in energy. It says here, if you read it, it says, shown below are graphs of velocity moving on a straight horizontal line, blah, blah, blah. So that means that there's no change in gravitational potential, right? So that means there would only be a change in what kind of energy? Kinetic, if there's work done. And kinetic is 1/2 mv squared, right? I should not make that an equal sign, but I should just say that 1/2 mv squared is the kinetic energy. And so I looked, okay, well, if I'm talking about changing kinetic energy, there's no change in kinetic energy here. If there's no change in kinetic energy, there's no work. Same here on D, okay? On C, I'm changing from 6 meters per second down to 0. That's a big change in velocity, which means it's a big change in kinetic energy as compared to just going from 2 to 6. Does that make sense? They're saying essentially the same thing, just looking at it in a different way. Neither one is wrong. They're both fine. The reason that I wanted to tell you that and not just say, good job, was because sometimes when you're doing problems, it makes more sense to look at it using the work equals force times distance. Sometimes it makes more sense, or it's easier to look at the work equals change in energy. So just kind of broadening your view, broadening your understanding to know that you can look at this in the same, like you can look at it both ways. Sometimes one makes more sense than the other. So anyway, there you go. But good job. You guys got it right. Nice work. Yeah.
I'm sorry, on a graph where it's velocity and time, you find force by finding the slope, right?
Say that one more time.
How do you
No, I want you to ask that question because it's a good question to ask.
I didn't even hear that.
I think I heard it, but I don't. Sometimes I hear a question and I just want to make sure that I'm understanding because I like to put words in. So ask the question that you were asking. I think you said.
Velocity and time.
Uh-huh.
How did you find the force?
So I didn't, but a lot of you did. So what is literally the slope of a velocity versus time graph, you guys? The acceleration, right? Acceleration, if you write this the way that we like to write it better, acceleration is equal to F net over m. Is that okay? And so if you know the acceleration, because that's the slope of the line, then, and the mass is staying the same the whole time, then as acceleration gets bigger, F net gets bigger. So I don't know the value of F net, but the beauty of these kind of questions is that I don't need an actual number. I just need comparisons. Does that answer the question that you were asking? Okay. Fantastic. All right. We're going to take just a couple of minutes to look at homework questions. Are there any? Maybe that's the first piece of the puzzle here. So this is chapter 10. They're listed up there, 13, 19, 30, and 31 questions, and then problems 4, 7, 61, 65. Any of those that you'd like to go through?
7.
Number 7? Cool, thanks. So this is chapter 10, problem 7. All right. Ooh, this one looks fun. All right, it says a crate. Shh. Just so that I know that you hear it, and I know that there are a couple people gone, so I want to make sure that we're really being respectful so everybody can hear and understand here. It says, a crate slides down a ramp that makes a 20-degree angle with the ground. Yay! To keep the crate moving at a steady speed, Paige pushes back on it with a 68 Newton horizontal force. How much work does Paige do on the crate as it slides down 3.5 meters on the ramp? All right. So let's draw this picture. So here's our ramp. That's a little more than 20 degrees, but we'll just kind of pretend. So 20-degree angle. So here is the crate. And it says that Paige pushes back on it. So it's sliding down. Is that right? And she doesn't want it to accelerate down. Am I understanding this right? Is that how you guys are understanding it? So she's applying a force like in this direction. Going like that. So she's probably standing down here, pushing. I don't really how you apply, whatever. Anyway, a horizontal force. It's a little strange, but we'll just go with it.
Doesn't
Okay.
matter what way it is. It's like straight up. Like right from the box, like with the angle.
Like where this, like if it's down at the corner, is that what you're asking?
No, like if it's with the angle of like if it's going out. Yeah, like straight in.
Like up here like this?
Yeah.
That would matter because then the force is being applied in a different direction relative,
It's still gonna be sliding.
Yeah, because it says that she's applying a force to keep it moving at a steady speed. Because if she wasn't applying that force, it would accelerate down the ramp, is I think how I'm understanding the question. So it says to keep the crate moving at a steady speed, she pushes back on it with a 68 Newton force. So the applied force is 68 Newtons. And it says how much work does she do as the So we want to know the work as the crate slides down the ramp a distance this way of 3.5 meters. Does that look like the right picture? What you guys have in your head? Okay. So I think what they're really getting at here is that we need to know the force, that the force and the distance have to be, what did we say yesterday? Do you remember? The same direction. So they need to either be parallel or they can be anti-parallel. That's a little bit weird because, what does that exactly mean? But it's kind of like we were talking about right at the very end yesterday. We were talking about like sliding that cheeseburger towards us. Even if it was moving at a constant speed, that means that I'm doing work, but then friction is doing negative work, right? So that the total work adds up to 0. But the thing that we know that we figured out yesterday, kind of quickly as things were moving on, was that it's force times distance. Your book says times the cosine of theta. I like to just call it parallel because that makes it more clear to me. So the force that she's applying in this direction, is that parallel to the displacement?
No.
It's not. So if Isaac was right and we could just put it right up that hill, if what he was asking was accurate, I shouldn't say that you were wrong, but the question that you were asking was going up this way, then it would be an easy problem, right? Then it would just be, she's applying a force of 68 newtons over 3.5 meters. Whatever, it's all good. But in this case, the only part of the force that's actually doing work is the force that's going in the same direction as the distance. Does that make sense? Question?
Wait, so would you just find the force in that direction, trade?
Yeah.
And
Trig it up? Yeah. It's a verb or a verb phrase or something. I don't know. That's what I would do. So let's break this into pieces like this. One like that. And then one like this. And we just want the applied force that is parallel to our ramp, right? So I'm thinking that this is the angle, that's 20, right? Am I doing my geometry right? Check me. Yeah? So in fact, it's going to be the force of, 68 newtons? Times, in this case, that would be the cosine of 20 times the distance of 3.5 meters. Is that okay? Any other ones that you want to go over? Questions that you have? Looking at the homework list. No is an okay answer. I just want to make sure that I'm making time.
61.
Sure.
Label for work is still joules, right?
It is still joules. Yes. Good question. Yes. The label for work and energy will always be joules. Yes. Yeah. Courtney, what did you say? 61?
Yeah.
Sure. Chapter 10, problem 61. All right. 61 says, how much work, does an elevator motor do to lift a 1,000 kilogram elevator to a height of 100 meters at a constant speed? All right. So here's my elevator. Oops, that's really not a very pretty elevator. You guys ever seen the elevators that you can see into and you can see the counterweights going down as the elevator's going up? That's what I was trying to draw, right? Because there's a motor up here that's with the counterweight, like that. Yay! All right. So the way that an elevator moves is that it's applying a force up, right? Okay, and that force up is, if it's moving at a constant speed, how does the force up compare to the gravitational force down?
Say that again.
Yeah, I will, because that was kind of a poorly worded question. How does the force up from the motor compare to the gravitational force down if the elevator is moving at a constant speed? Equal, right? F net has to be 0. So the motor's going up while gravity's pulling down. Life is good. Now, they specifically said that it's moving at a constant speed, because if you're moving faster, then you got to apply a little bit more force, right? If you're moving if you're accelerating. If you're decelerating, if you're slowing down, then it's going to apply a little less force. This is exactly why, friends, I really want you guys to stop wasting my markers and what I feel like is ignoring my conversation. And if you don't need my conversation, that's fine, but I don't want you to blatantly ignore it. I appreciate it. Thanks so much. When you get into an elevator and it starts moving, a little in your tummy, right? That's like, oh, I'm accelerating. And then you're riding, zip. I'm decelerating or accelerating negatively, right? That's exactly what's happening, right? So your stomach is like an accelerometer. You just didn't know it. That's exactly what it's doing. So anyway, just beside the point there. Okay, anyway, moving on. How much work does it do? Well, that's a good question. So there's a force. So we've got the force of the earth on the elevator. And you got the force of the motor on the elevator. And we know that F net is equal to F of the motor plus the force of the earth, which adds up to 0. Do I have to write all that out just to figure out the number? Probably not. But is it nice to be able to see that and remember that and remind ourselves that all works? Yeah. For sure. All right. So we are doing work. Which means we've got a force acting over a distance. The force and the distance have to be parallel. And in this case, by golly, they are. The distance, what did they say, was 100 meters? Is that right? 100 meters. The force that's being applied, how are we going to find that? Solve for FG and then plug that in for FM, right? I'm going to totally, because I'm lazy and I'm trying to move fast, I'm going to totally pull a Harrison and make G 9.8, or excuse me, not 9.81, but just 10. Does that sound okay? Oh, that's Rudy. I'm sorry. It's like you're his spokesman or something. I don't know. There's some sort of I don't know, PR thing going on over there. Anyway, I don't know. Anyway, so I'm going to totally do that. I'm not going to try and attribute it anymore. Someone. Okay. So we can find mass times acceleration due to gravity. Again, I'm just going to be, I don't want to say lazy. I'm going to be efficient. So 1,000 kilograms. You're right. Yeah, I know, right? Speaking of PR, yeah. 1,000 kilograms times 10 meters per second going down. Oh, that one's going down, so that means this one has to go up. Oh, I can multiply that in my head with no problem. That's so easy. I mean, I probably could have multiplied the other one anyway, too, because it's all zeros, but that's okay. All right, so we've got 1, 0, 0, 0, 0. Did I get enough zeros? 1,000 times 10 is 10,000. Yeah? Nice. And it's Friday afternoon. It's a little hard to remember. So it's 1,000. What's that?
Is that in the textbook? Is that a given?
What is what a given?
Henry stuff.
Are you trying to, do you have a genuine question?
Yeah.
I don't know what just happened.
She's talking really fast.
I am, because we've got lots to do today. Okay, so 10,000 newtons of force acting over 100 meters. Add 2 more zeros to that, right? Indeed. Bless you, bless you, bless you. Oh my goodness, there's so much sneezing that's happening here.
One megajoule.
Indeed. All right. How are we doing? We okay? That's just a lot of zeros. Shh. Oh, yeah, and then part B starts to talk about power as well. So part B says, how much power must the motor supply to do this in 50 seconds? In 50 seconds. So we're just going to remind ourselves, have a great weekend, Megan, that power is equal to work over time. So you've got, what was that? I didn't even make it is 1 million, isn't it? 1, 2, 2, 2. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Did I write that right? Yeah. Divided by 50 seconds. Seconds. Joules per second, also known as
Watts.
What? What? Yeah. All right. How are we doing, team? Thank you. Gotta rely on that drummer to, give you the rim shot. What's up?
I also do part A is,
Hold on, friends, I can't hear. Say again?
you also do part A is finding huge energy, so you find the potential energy. That's it. That's huge.
Done. Yes. Because you can go H equals 0 wherever you want, right? Yeah. Did you guys catch the question?
It was about kinetic energy.
It was not kinetic. It was potential because our kinetic energy isn't changing. But so Nick said, hey, but couldn't I just use your silly trick from earlier and say that work is also equal to the change in energy? And in this case, because it's at a constant speed, my kinetic energy isn't changing, but my gravitational potential is. So that's a change in gravitational potential, which is really just m times g times change in h. Yeah? And friends, look at this, right? Force is mg. Do you see this? This is so lovely. Thanks for asking the question so we can point it out. This is so nice.
Distance is 8.
I know, right? That's so cool. mg, mg, mg. It's right there, boom and boom. Right? And then d is just h. Look at this symmetry. It's so cool. Oops, I can't highlight that in blue. There's D, there's H. Oh, that's really
Whoa,
good.
that's cool.
You're welcome. All right. How are we doing? Are we okay?
We're solid.
Fantastic. More questions?
When you do the thing where you try to do it, it's right.
Some things take practice. You can't always be good at everything all the time, right? Yeah. All right. I'm ready to move on. You guys ready to move on? Is that okay? Sweet. All right. Here we go. So, as a physics teacher, some things that you buy, like when you're trying to outfit a brand new school with equipment, some things that you buy are like, you use them for a lot of things, like carts and tracks and things like that. Some things are used for one thing, and this is one of them. Actually, we'll use this for 2 different labs, but they're both related to the exact same thing. And the thing we're going to use this for is to study Hooke's law. And you know what? When you order this, when you put it actually in the catalog and you're like, I want this, you literally look up Hooke's law apparatus. Like that's literally what it's called. So let me show you this. It's really not technical, but for some reason we think that we need it. It's a little ring stand with this little cute, it's a hook. That's not why it's called Hooke's law though. Hooke's law is actually named after a guy named Hooke. Okay. And I've mentioned to you a few times that I'm not a huge fan of Isaac Newton. And one of the myriad reasons that I don't love Isaac Newton is because he was in charge of the Royal Society, which was like where all of the scientists would vet their papers. Like this is, way pre, like having all different kinds of professional publications and things. And he was really mad at Hooke because Hooke wanted to had this idea and wanted to get it out there. And Newton was also trying to study the same thing at the same time and was a little bit behind him. But see, the problem was that Isaac Newton was in charge. And so they didn't have, pictures back then, but they had paintings, right? All of the Royal Society members had their paintings up on the wall, blah, blah, blah. Hooke got rid of his. So there is no documentation as to what this guy named Robert Hooke looks like because Isaac Newton basically kicked him out of the Royal Society and got rid of and burned all of his stuff.
That's cool.
He is no longer part of existence except for now. Right? What's that?
You need to make a movie out of it.
I know, right? Somebody probably did. I just haven't seen it. So anyway, Robert Hooke, not known for inventing calculus or anything wild like that. He really he did a lot of things, but the thing that we talk about is the spring stuff. So we're going to study springs today, and you are going to establish Hooke's law. That's what your job is today. So, little ring stand with a little hook here, and then you've just got a nice handy-dandy little ruler that if you squeeze the back, it can move up and down, which is, helpful. So that's all cool. And then you've got a spring. Now, a couple of things about these springs. Many of you probably had slinkies when you were a kid or have slinkies now, and then you probably either had a younger brother, sister, cousin, somebody at your house, or you were that kid, okay? And you stretched them and you cracked whatever. These ones are really sensitive. They will break. Don't break them, okay? I charge an extra premium if you break my, right? They don't actually cost very much, but I'll charge like a 5,000% markup or something crazy like that. Anyway, so be careful, okay? So don't overstretch them. Don't play with them and stretch them. Don't mess with them, okay? So the cute little spring is gonna fit right here, directly on this cute little hook. And then you're gonna put weights on it. And the question is, how does the mass on the spring, so there are gonna be some cute little slotted weights that will sit right on there. And then you're gonna find out how it affects the displacement from equilibrium. Equilibrium being the stretch amount that it is right now. Okay, that's all you need to do. It's pretty straightforward, pretty easy. Simple lab, but the results are very important, and that's why we're actually going to use this to do things. So I want you to actually get some really good data. Think carefully about your design and data collection. By the end of the period today, I don't think it should be a problem. You need to produce a handwritten design and data collection and processing, that should say processing portion of the write-up. So you're just going to write this out, and then you're going to collect some data, and then you're going to graph it, and that'll be it, okay? Should be pretty straightforward, not a super difficult experiment to do. I'm not going to hand this to you because that's literally what it is. So if you want to write down how does the mass of a spring or on a spring affect its displacement, that's the big question. And then I'll leave this up so you can take a look at it. I want you to define your problem. Tell me how you're going to control variables. Tell me how you're going to collect data. You don't need lots and lots of trials, you guys, because it's just going to sit there. It'll be fine. Okay? You're going to record your data, including units. We just haven't done this for a while, so I just want to remind you. We're going to process the raw data, if there's any processing you need to do, and then you're going to graph it. Okay? Sound doable? No?
We have like partners or groups.
There are 7 setups, so make that work. Does that sound good? Okay? Groups no bigger than 3, 4? No bigger than 4. 1, 2, 3, 4, 5, 6. Yeah. All right, go.
The best handwriting. Yep.